Deep beneath Mount St. Helens, 7,500 feet down, the Earth is stirring with a restless force. GPS stations bolted to the slopes show the ground rising, tilting outward by millimeters each month. Seismometers scattered across the mountain are recording tremors that pulse through the rock every few hours, shallow at first, then deeper. For 40 years, scientists have monitored this volcano like a patient in intensive care. They know its moods, its cycles, the way magma telegraphs its intentions through cracks in the crust. After the catastrophic eruption of 1980, the USGS built one of the most sophisticated volcano monitoring networks on Earth here. The data from that network painted a clear picture. Mount St. Helens follows patterns. Inflation before eruption. Drumbeat earthquakes when the dome grows. Long pauses between episodes of unrest, sometimes years. Yet now, the volcano is defying every expectation, rewriting the rules they thought they understood. The mountain sleeps. From the air, Mount St. Helens looks like a monument to violence frozen in time. The horseshoe crater yawns open to the north, a raw wound carved by the 1980 blast that removed 1,300 feet of summit. Inside, a lava dome rises 876 feet above the crater floor, built grain by grain between 2004 and 2008. For the last 16 years, that dome has been silent. Snow fills the crater each winter. Meltwater carves channels through ash. Glaciers creep back across the slopes, rebuilding ice fields that were vaporized decades ago. Hikers return to the trails, cameras aimed at a landscape that looks almost peaceful. The mountain's last eruptive period ended in January 2008 with a quiet extrusion of lava, then nothing. Seismicity dropped to background levels, a few small quakes per month, most too faint to feel. For nearly 2 decades, Mount St. Helens has done exactly what a dormant stratovolcano should do. Beneath that stillness, something has been stirring for months. The first tremors. The first anomaly appeared in late 2023. A swarm of small earthquakes, magnitude 1 to 2.5, clustered 4 to 6 miles beneath the crater. Not unusual by itself, Mount St. Helens averages 10 to 20 detectable quakes per month. But these were different, tightly grouped in time, rhythmic, and deeper than the shallow fracturing that marks dome building. By February 2024, seismologists at the Cascades Volcano Observatory noticed the swarms were accelerating. What had been 3 or 4 quakes per week became 12, then 20. The epicenters traced a narrow column through the crust, not scattered randomly, but stacked vertically, like beads on a string. The waveforms showed long-period oscillations, the kind generated when pressurized fluid moves through rock. They flagged it, ran the data against historical records from 2004, from 1980, from the mountain's last 11 eruptive episodes. The depths matched known magma pathways, but the frequencies were off, too slow, too sustained. By March, the swarms had migrated upward by half a mile. Within weeks, the tremors weren't just increasing, they were changing. The instrument's wake. GPS stations scattered across the flanks began recording movements measured in millimeters. Ground that had been still for decades was shifting, rising on the mountain's north face at rates that doubled every week. Tilt meters buried beneath the snow showed the summit wasn't just moving upward, it was tilting, as if something beneath was pressing against the underside of the Earth. Gas sensors downwind picked up spikes in sulfur dioxide, invisible plumes drifting east toward the valleys. Thermal cameras mounted on distant ridges detected heat blooms near the crater rim, signatures that appeared and vanished over hours. Each instrument offered a fragment, a millimeter here, a temperature shift there, a whiff of gas carried on the wind. Seismometers 30 miles away recorded low-frequency tremors that persisted for minutes, then hours, vibrations too sustained to be tectonic fractures. Satellites measured the mountain's surface swelling by 3 centimeters in a single month, a deformation visible only from orbit. Every monitoring system across the Pacific Northwest was converging on the same conclusion. Something was moving beneath the volcano, and it was accelerating. But the real alarm came from what the instruments couldn't explain. Magma's fingerprint. Magma has a signature. When it rises, it doesn't just shake the ground, it hums. The tremors produce a harmonic frequency, a sustained vibration distinct from the sharp jolts of tectonic quakes. It's the sound of molten rock forcing its way through fractures, of gases escaping under pressure, a resonance geologists call volcanic tremor. You can see it on a seismograph as a dense, continuous wave rather than discrete spikes. Then there's the inflation. Magma doesn't compress. When it accumulates beneath a volcano, the surface above must rise to make room. GPS arrays measure that uplift in 3 dimensions, mapping how the mountain swells and where the pressure originates. Gas ratios tell another part of the story. Fresh magma releases sulfur dioxide and carbon dioxide in specific proportions. Old magma, reheated groundwater, tectonic stress, each leaves a different chemical trace in the steam vents. By April, St. Helens was showing all 3 signatures simultaneously. The harmonic tremor, the radial inflation centered 4 miles beneath the summit. The gas chemistry consistent with new magma at depth. It was a textbook case, except for one detail. The tremors were migrating laterally, not vertically, spreading beneath the mountain in directions magma doesn't normally travel, and the fingerprint they found beneath St. Helens didn't match anything in the textbooks. May 18, 1980. On the morning of May 18, 1980, a 5.1 magnitude earthquake triggered the collapse of St. Helens' north face. 1 cubic mile of rock slid downslope at 110 miles per hour, the largest landslide in recorded history. The debris avalanche exposed a pressurized magma chamber that had been building for months. What followed wasn't an upward eruption, it was a lateral blast. The explosion traveled north at 300 miles per hour, flattening 230 square miles of forest in seconds. Trees 6 feet thick were snapped like matchsticks, stripped of bark and branches, laid parallel in rows extending 17 miles from the summit. Pyroclastic flows, mixtures of gas and pulverized rock heated to 1,300 degrees Fahrenheit, roared down the valleys at 80 miles per hour. 57 people died, most of them miles beyond the evacuation zone, buried or incinerated before they could flee. The eruption column rose 15 miles into the stratosphere, depositing ash across 11 states. The summit, once 9,677 feet, was reduced to 8,363 feet, leaving a horseshoe crater a mile wide. Rivers choked with mud. Towns went dark under inches of ash. It remains the deadliest volcanic event in U.S. history, the only eruption most Americans have lived through. That eruption taught scientists what St. Helens could do. What's happening now is teaching them what they missed. The bulge. In the spring of 1980, surveyors measured the north face of St. Helens every morning. They watched it swell outward at 5 feet per day, a geological hemorrhage visible to the naked eye. The bulge grew 450 feet, a blister of magma pressing against the mountain's skin. They knew it would fail. They didn't know when. Each day bought time to widen the evacuation zone, and each day raised the odds that today would be the day. The governor ordered roadblocks at the 5-mile perimeter, then the 10-mile line, then 15. Some residents refused to leave. A geologist named David Johnston volunteered to staff the closest observation post 6 miles north on Coldwater Ridge. He radioed his measurements twice a day. On the morning of May 18th, the bulge finally ruptured. Satellite data from last month revealed something growing again, but not where anyone expected. The deep source. The new seismic swarm isn't coming from the shallow magma chamber that fed the 1980 eruption. That chamber sits 4 to 7 kilometers down, a reservoir geologists have mapped in detail for 44 years. The tremors are originating 15 to 20 kilometers beneath the surface, in the lower crust where the continental plate meets something hotter. Seismometers triangulated the source within a 3-kilometer cube. The signals show low-frequency harmonic tremor, the signature of fluid movement through rock, not water. magma, pushing upward through a network of fractures that wasn't supposed to be there. The 1980 eruption drew from a pre-existing chamber. This is fresh melt rising from the mantle, carving a new pathway. It could stall and cool. It could feed the old chamber and trigger a familiar eruption, or it could bypass the shallow system entirely and force open a new vent. Depth changes everything about how an eruption unfolds. The Cascade Arc, St. Helens, is one link in a 700-mile chain. The Cascade Arc stretches from Lassen Peak in Northern California to Mount Baker near the Canadian border. 18 major volcanic peaks and hundreds of smaller cones, all of them fed by the same engine. 100 miles offshore, the Juan de Fuca Plate slides beneath North America at 4 centimeters per year. It carries seawater down into the mantle, where heat and pressure squeeze the water out of the rock. That water lowers the melting point of the mantle above it, creating pockets of magma that rise through the overriding plate and pool beneath the mountains. Rainier erupted 1,000 years ago. Hood last erupted in 1866. Shasta's summit fumaroles still vent sulfur gas. The entire arc is geologically active, an unbroken conveyor of subduction-fed fire stretching the length of 3 states, but they don't all behave the same way. St. Helens sits at a unique junction in that arc, and that may be why it's reacting first. The subduction engine, the engine driving all of this, sits 50 miles beneath your feet. The Juan de Fuca Plate, a slab of dense oceanic crust, slides eastward under North America at 4 centimeters per year. As it descends into the mantle, temperatures climb past 1,200 degrees Fahrenheit. But it's not heat alone that creates magma. The descending slab carries seawater, locked-in minerals formed on the ocean floor. At depths between 60 and 100 miles, pressure squeezes that water out. It rises into the wedge of mantle rock above the slab. Water lowers the melting point of rock by several hundred degrees. The mantle begins to melt in droplets, then pools. Magma, lighter than the surrounding stone, finds fractures and rises. The journey from slab to surface takes between 50 and 200 years. This process has been stable for millions of years, feeding the Cascades on a geologic clock. Recent ocean floor surveys found something unexpected along the subduction zone offshore. The plate's pulse. Seafloor instruments deployed in 2021 recorded a cluster of micro-earthquakes along the plate interface, 200 miles west of the Oregon coast. They were small, magnitude 2 to 3.5, but their pattern was unusual. They migrated north over 6 weeks, tracing a line parallel to the trench. At the same time, GPS stations on the coast detected millimeter-scale shifts, a signature of what geologists call a slow slip event. The plate releases accumulated strain not in one violent jolt, but in a creeping unlocking that can last days or months. The last comparable event in this section of the zone was in 2008. Some researchers argue the plate's descent angle may be steepening, a change too gradual to detect over human lifetimes, but measurable with decades of seismic data. Others point to variations in slab velocity, fractions of a millimeter per year that compound over the width of the plate. The debate is ongoing. If the plate is changing its rhythm, every volcano above it will feel the consequences. The sister volcanoes. Mount Rainier, 50 miles north of St. Helens, rises 14,411 feet above Puget Sound. Its glaciers hold more ice than all other Cascade peaks combined. 27 seismometers ring its base. For 18 months, they registered nothing abnormal. Background noise, seasonal ice shifts, the occasional rockfall. Mount Adams, 35 miles east, is quieter still. Mount Hood in Oregon shows steady low-level seismicity, a baseline hum that hasn't changed in a decade. Mount Shasta in California had a brief swarm of shallow quakes in July 2023, then silence. On paper, the arc looks stable. But seismic networks don't cover every peak equally. Rainier and St. Helens have dense arrays. Adams has 6 stations. Glacier Peak in northern Washington has 4. The farther you get from population centers, the coarser the data becomes. You can miss a lot in the gaps. Mount Rainier's sensors picked up an anomaly 3 weeks after St. Helens began acting up. The inflation map. INSAR satellites painted a different picture when they turned their full attention to St. Helens. The summit was rising, yes, but the north flank was subsiding 1.2 centimeters per month, while the southeast shoulder bulged outward at twice that rate. GPS stations embedded in the rock recorded millimeter-scale shifts every 6 hours, and the pattern changed depending on where you stood. This wasn't a simple inflation like a balloon filling with air. The mountain was warping in sections, some zones compressing while others stretched. The north crater rim tilted 0.8 degrees westward over 9 days, then paused, then resumed at half the speed. The deformation map looked organic, asymmetric, alive. A single magma pulse would produce concentric rings of uplift radiating from the source. What the instruments recorded instead was a patchwork, zones of movement that didn't share a center. The data suggested multiple pressure sources at different depths, each pushing in its own direction. Geologists compared this pattern to every eruption in the historical record. It matched none of them. The gas plume. You can't see sulfur dioxide with the naked eye, but a spectrometer mounted on a helicopter can. Overflights in late April measured 340 metric tons of SO2 venting from the crater per day, up from 12 tons the month before. Carbon dioxide emissions climbed in parallel, invisible plumes rising into the cold air and dispersing downwind toward the Spirit Lake Basin. Gas escapes magma as pressure drops during ascent. The deeper the source, the more CO2 dominates because it exsolves first, at 30 kilometers or more. Sulfur dioxide breaks free closer to the surface, typically below 10 kilometers MOV. The mix tells you how far the magma has traveled and how fast it's moving. High SO2 means shallow storage, a reservoir nearly ready to breach. St. Helens was exhaling both in quantities that didn't line up with a simple ascent from a single chamber. The CO2 flux spiked independently of the SO2 on May 2nd, then the two synchronized again 4 days later. Gas geochemists ran the numbers through degassing models and got contradictory outputs. The ratio of gases suggests something is mixing deep below, 2 magma bodies perhaps, or something older rising to meet something new. The magma reservoir. Seismic tomography mapped the plumbing years ago. A shallow magma chamber sits 5 to 10 kilometers beneath the summit, a lens of partially molten rock, maybe 15 kilometers wide and a few hundred meters thick. Below that, starting around 15 kilometers depth, a much larger reservoir sprawls through the crust, a zone where melt fractions range from 5% to 30%. Dikes and sills connect the two, narrow channels that let magma migrate upward when pressure builds. This is how stratovolcanoes breathe. Magma accumulates in the deep reservoir for decades or centuries, crystallizing, evolving, waiting. When fresh melt arrives from the mantle wedge below, it heats the stored magma, reduces its viscosity, and drives it toward the surface. The shallow chamber acts as a staging area, the last stop before eruption. The system had been quiet since 2008. The shallow chamber cooled and solidified into a plug of crystal mush. The deep reservoir showed no signs of recharge, no seismicity, no deformation. For 16 years the mountain slept. Seismic imaging from last week showed the deep reservoir is no longer isolated. The conduit opens. The new seismic data revealed something USGS geophysicists had been watching for since October. A vertical pathway was forming between the deep reservoir, 8 kilometers down, and the shallow magma chamber at 4 kilometers. Not a solid column of molten rock yet, but a network of fractures widening under pressure, filled with superheated fluids and crystals suspended in melt. This is how connectivity begins. The deep reservoir contains dacite magma at 850 degrees Celsius, viscous and gas-rich. The shallow chamber holds older, cooler material at 750 degrees Celsius. When a conduit opens between them, the pressure differential drives fresh magma upward at rates measured in meters per day. The shallow chamber inflates. Gas bubbles nucleate and expand. Seismometers recorded the signature on February 3rd. A swarm of long-period earthquakes clustered along a vertical plane beneath the summit, depths ranging from 7.2 to 4.6 kilometers. The events weren't sharp, brittle cracks. They were slow ruptures, the kind caused by fluid movement through rock. The conduit was no longer theoretical. By February 9th, GPS stations on the summit had risen 11 centimeters. The volcano was breathing. But that's only half the story. The conduit isn't just rising, it's branching. The lateral intrusion. On February 12th, a second swarm appeared, this one horizontal. Earthquakes traced a line spreading northeast from the main conduit at a depth of 3 kilometers, extending 2.4 kilometers beneath the edifice. Then another to the east-southeast, shallower, at 2.1 kilometers depth. The magma wasn't just climbing, it was spreading laterally, intruding into horizontal fractures and sills beneath the north and east flanks. INSAR imagery confirmed what the seismometers suggested. Ground deformation on the northeast flank showed a bullseye pattern centered 1.8 kilometers from the summit, uplift totaling 19 centimeters since late January. The pattern matched models of a horizontal sill inflating under pressure. The geometry was hauntingly familiar. In 1980, magma intruded laterally into the north flank for weeks before the eruption, creating a visible bulge that advanced outward at 1.5 meters per day. The current intrusion is deeper, larger in volume, and advancing faster. Tiltmeters show the northeast flank is steepening. The edifice is being pried apart from the inside. Lateral intrusions are unstable. They pressurize the flank until the rock fails, suddenly and catastrophically. If that lateral intrusion reaches the surface, it won't erupt upward, it will erupt sideways. The 1980 blast zone, May 18, 1980, 8:32 a.m. The north flank collapsed in the largest landslide in recorded history, removing 2.8 cubic kilometers of the summit in 15 seconds. The lateral intrusion, suddenly uncapped, exploded outward at 670 miles per hour. A superheated blast of rock, ash, and gas at 680 degrees Fahrenheit spread across 230 square miles in under 3 minutes, moving faster than anything in its path could run. Trees 6 feet in diameter were snapped off at the base and swept away like grass. The blast wave jumped ridges and valleys, scoured the ground to bedrock, then kept going. Geologist David Johnston was stationed 6 miles north on Coldwater Ridge, considered a safe observation point. His last radio transmission was Vancouver. Vancouver, this is it. His body was never found. 57 people died that morning. Most were outside the official exclusion zone, some as far as 13 miles from the summit. The lateral blast wasn't modeled in the evacuation plan because no one had seen one before. Spirit Lake, a popular recreation area, was buried under 200 feet of debris. Cabins, campgrounds, logging camps, all erased in seconds. The blast zone remains largely barren 45 years later, a gray scar visible from satellites. The communities downwind today are 10 times larger than they were in 1980. The evacuation calculus. Cowlitz County's emergency director sits in a room lined with monitors, studying GPS displacement graphs and seismic plots. The decision tree is brutal. Evacuate too early and you've displaced 80,000 people, shuttered timber mills, closed I-5, cost the region $200 million a week for what might be a false alarm. Wait too long and the roads clog. The panic spreads. People die in their cars trying to flee. In 1980, the evacuation zone held 3,000 residents. Today, it would be 40,000, most of them newcomers who never saw the ash fall, never heard the roar. Every briefing from USGS comes hedged with probabilities, confidence intervals, caveats. The science can tell you magma is moving. It cannot tell you when the mountain will let go. Public trust is finite. Cry wolf once, and the second warning goes unheeded. But the data arriving daily is forcing their hand. The harmonic tremor. Seismometers don't just record earthquakes, they capture everything the Earth does, every vibration, every pulse. And for the past 2 months, station STH-3 on the volcano's north flank has been recording something else entirely, a signal that doesn't stop. It's called harmonic tremor, not the sharp jolt of a quake, but a sustained hum, a drone that can last hours or days. It's the sound of fluid forcing through rock, magma and gas, carving pathways upward. The frequency is low, between 1 and 5 Hz, below the threshold of human hearing, but unmistakable on a spectrogram. Mount St. Helens went silent for 18 years after its last dome-building phase ended in 2008. The tremor returned in early September. Faint at first, intermittent, then constant. Now it runs 24 hours a day, a ceaseless vibration radiating from somewhere beneath the summit. Last Tuesday, the tremor's frequency shifted. It got deeper and louder. The ice quakes. There's ice in the crater, remnants of 11 small glaciers that cling to the horseshoe rim and spill onto the lava dome below. They've been there since the mountain cooled, fed by cascade snow, creeping forward centimeters each year. In October, seismometers began picking up a new signature: sharp, shallow, clustered. Ice quakes. The glaciers are fracturing. Meltwater pooling beneath the ice refreezes and expands, cracking the matrix. Thermal stress from below causes the surface to buckle and slide. The signals are small, magnitude 0.5 or less, but they're multiplying. 12 events in October, 47 in November, 89 so far this month. Thermal cameras mounted on Johnston Ridge show the crater floor glowing faintly in infrared, warmth bleeding through ash and rock. The ice is thinning, carving into the crater lake, turning to slush at its base. What took decades to accumulate is vanishing in weeks. Glaciologists estimate the crater ice could be gone within 6 months. The question is what that will expose. The lava dome. Inside the crater, a structure has been sitting quietly for 20 years. After the 2004 eruption, dacite magma pushed through the vent, thick as toothpaste, barely flowing. It cooled into a dome 350 meters across, a solid plug of rock sealing the conduit beneath. For years, it just sat there. Surface temperature held steady at 45 degrees Fahrenheit, same as the surrounding rock. Then in November, thermal cameras picked up a change. The dome's eastern edge was reading 72 degrees Fahrenheit, then 89 degrees Fahrenheit, then 112 degrees Fahrenheit. By January, entire sections were glowing at 160 degrees Fahrenheit. Heat is rising from below, conducted through hundreds of meters of solid dacite. The plug is warming from the inside out. If the dome fails, the vent beneath it is open. The cryptodome. There's a structure more dangerous than a dome. A cryptodome forms when magma intrudes horizontally beneath the surface, never breaching, just inflating the overlying rock like a blister under pressure. You can't see it, you can only measure the bulge. In March 1980, the northern flank of Mount St. Helens swelled outward at 1.5 meters per day. The cryptodome beneath it held 0.11 cubic kilometers of pressurized dacite. When the slope failed, the release was instantaneous. 57 people died in the lateral blast. Seismic imaging now shows a low-velocity zone 800 meters beneath the crater floor. The signature matches viscous magma under compression, horizontally emplaced, deforming the rock above it. Ground-penetrating radar suggests it's already larger than the one that failed in 1980. The fracture network. The mountain isn't solid. Decades of eruptions have left it fractured. A network of cracks and faults threading through the edifice like spiderwebs in concrete. Magma doesn't carve new paths. It finds the weaknesses and forces them wider. Strain meters show the current intrusion is reactivating fractures that haven't moved since 1980. Old faults are slipping, opening by millimeters per day. New fractures are propagating outward from the cryptodome, radiating through the dacite like cracks in glass under stress. GPS arrays track each one. Most run vertically, venting pressure upward toward the crater. but fractures follow the path of least resistance, and the northern flank is already compromised. One fracture in particular runs from the cryptodome straight to the northern flank. The hydrothermal system. Beneath the cryptodome and the fracture network lies something else entirely. A hidden ocean of superheated water, threading through porous rock, pooling in ancient cavities, circulating in slow convective loops. This is the hydrothermal system, and it's vast, reaching kilometers deep, fed by snowmelt and groundwater, seeping down through the mountain's skin. The water dissolves minerals as it moves, silica, sulfur, iron. It builds pressure in sealed chambers, expands as it heats, searches for escape routes through the fractured rock above. When magma rises into this system, the water boils. Steam pressure can exceed the strength of surrounding rock in minutes. The result is a phreatic eruption, steam-driven, explosive, capable of blasting through hundreds of meters of rock even when no fresh magma reaches the surface. These eruptions don't need a magma conduit to open. They only need heat, and right now, the cryptodome is pressing into the base of the hydrothermal system like a brand. Temperature sensors in the crater's fumaroles are climbing, the water is boiling. The phreatic risk. Phreatic eruptions are among the most dangerous events a volcano can produce. They strike without the warning signs that precede magmatic eruptions. No lava, no incandescent fountains, just superheated steam tearing through rock at supersonic speed, hurling boulders the size of cars across kilometers. In 2014, a phreatic blast on Mount Ontake in Japan killed 63 hikers in seconds. They had no warning. The mountain looked calm, the skies were clear, and then the summit exploded. At Mount Ruapehu in New Zealand, a phreatic eruption in 2007 threw a 2-ton block 2.5 kilometers from the crater. At St. Helens, the hydrothermal system sits directly beneath the most fractured part of the edifice. The threshold for a phreatic blast is measured in degrees and pressure gradients. Once the water temperature exceeds its boiling point at depth and the confining pressure drops, even a small earthquake can trigger catastrophic flash boiling. The system becomes a loaded gun. Any fracture propagating into a sealed hydrothermal chamber could pull the trigger. But a phreatic blast would only be the opening act. The magma composition. What matters now is what kind of magma is rising. Chemical composition determines everything: how fast it flows, how much gas it holds, how violently it erupts. The 1980 eruption was dacite, a viscous, silica-rich magma that traps dissolved gases like a shaken bottle of soda. Pressure builds until the cork blows. Dacite eruptions are explosive. Gas bubbles can't escape the thick magma, so they expand catastrophically when pressure drops, fragmenting the magma into ash and pumice. Compare that to basalt, the fluid lava that oozes from Hawaiian volcanoes in glowing rivers. Basalt releases gas easily. It flows, it fountains, but it rarely explodes. St. Helens doesn't make basalt. The cryptodome forming now carries the same chemical signature as 1980. High silica, high viscosity, high gas content. Chemistry is destiny, and this chemistry built the blast that removed 400 meters of mountain and sent a lateral surge across 600 square kilometers at 1,080 kilometers per hour. If the rising magma matches that composition, the mountain is priming for a repeat. But samples from the deep tremors suggest a second magma type is involved, something hotter and more primitive. The mafic injection. Geochemists call it mafic injection. Basaltic magma, fresh from the mantle at 1,200 degrees Celsius, punches upward through the crust and collides with the cooler dacite reservoir sitting 6 kilometers beneath the summit. The basalt is fluid, primitive, loaded with dissolved gas. The dacite is viscous, evolved, already saturated. When they meet, heat floods into the dacite. Crystals begin to dissolve. Gas bubbles nucleate along the contact zone. The dacite expands, fractures propagate, pressure spikes. What was stable becomes unstable in hours, not years. This isn't speculation. Seismic tomography shows a vertical conduit connecting deep, low-frequency tremors to the shallow cryptodome. Gas ratios from fumaroles have shifted toward mantle signatures. The sulfur dioxide flux doubled in 11 days, then plateaued, a pattern consistent with fresh magma stalling just below the older reservoir. Every major eruption in St. Helens's history began with this kind of mixing. The eruptive history. The mountain has erupted at least 22 times in the past 4,000 years. Roughly once every 100 to 300 years, it wakes. Some eruptions were quiet, extruding thick lava domes that cooled in place over months. Others were Plinian, sending ash columns 25 kilometers into the stratosphere and burying valleys under pyroclastic flows. Between 1800 and 1857, St. Helens erupted continuously in what geologists call the Goat Rocks eruptive period. Lava spines grew and collapsed. Ash fell on settlements 80 kilometers away. Then the mountain went silent for 123 years, long enough for forests to reclaim the slopes and for people to forget what it could do. The 1980 eruption was a lateral blast, rare but not unprecedented here. The 2004 to 2008 sequence was effusive, building a new lava dome inside the crater with almost no explosive activity. The mountain's behavior shifts with magma composition, gas content, and the geometry of the plumbing system feeding it. But none of those past eruptions were monitored in real time. This one is. The monitoring web. The Cascades Volcano Observatory runs 53 seismometers around St. Helens, arranged in concentric rings from the crater to 15 kilometers out. GPS stations measure ground displacement to the millimeter. Tiltmeters track changes in slope angle. Gas sensors sample fumarole emissions twice a week, hunting for shifts in CO2, SO2, and helium-3 ratios that betray magma depth. Satellite radar sweeps the edifice every 12 days, building interferograms that reveal inflation invisible to the eye. Webcams stream live video. Thermal cameras map heat signatures in the crater. The data flows into servers in Vancouver, Washington, where algorithms flag anomalies and route alerts to volcanologists on call. It's the most instrumented volcano in the Cascades, more densely watched than Rainier or Hood. Scientists can see the mountain breathe. They can trace seismic waves from their source to the surface, map the geometry of magma bodies, measure deformation down to fractions of a degree. They know more now than they've ever known. Last night, 3 separate instrument networks recorded the same anomaly at the same moment. The anomaly. At 11:47 p.m., a seismometer 8 kilometers north picked up a low-frequency tremor lasting 90 seconds. At 11:52, GPS stations on the crater rim recorded 1.2 centimeters of vertical uplift. At 11:56, a COSPEC instrument at Johnston Ridge measured a sulfur dioxide spike 400% above baseline. 3 signals, 3 instruments, 10 minutes. This is the fingerprint of a magma pulse rising through the conduit, pressurizing the overlying rock, forcing gas ahead of it, through fractures, into the atmosphere. It's not subtle, it's not ambiguous. It's the signature geologists have been waiting for since the monitoring web went live, the confirmation that the system isn't just rumbling, it's feeding. The pulse traveled 4 kilometers in under an hour. Statistically, the next pulse should arrive within 2 weeks. The precursors. Seismicity has climbed from 2 events per day in January to 47 per day this month. Ground deformation shows the north flank inflating at 3 millimeters per week. Gas emissions have tripled since March. Sulfur dioxide now appearing in concentrations not seen since 2006. Thermal cameras detect a 12 degrees Celsius anomaly beneath the glacier on the crater's western edge. The snowpack is thinning where it shouldn't. The water is warmer downstream. Every textbook precursor is present. Escalating tremors, swelling ground, rising gas, heat bleeding through ice. The sequence is unfolding exactly as the models predicted, exactly as it did in the months before the 2004 dome-building eruption. The only precursor still missing is the one that gives you hours, not days. The swarm escalation. In February, seismometers recorded 4 earthquakes. In March, 89. In April, 312. The swarms aren't just increasing, they're accelerating, magnitude creeping upward from 0.8 to 2.1 to 3.4. Each cluster marks a fracture event, magma forcing its way through cold rock, shattering the crust grain by grain, carving new pathways toward the surface. The hypocenters are migrating. February's swarms originated at 7 kilometers depth, March 5 kilometers, April 3.8. The mountain is breaking itself open from the inside. Every swarm is another step closer, another boundary crossed, another barrier that won't hold the next time. Yesterday's swarm reached within 2 kilometers of the surface. The alert level. The USGS uses 4 alert levels to track volcanic threat. Normal means routine monitoring. Advisory means elevated unrest. Watch means escalation toward an eruption or ongoing minor activity. And warning means an eruption is imminent or underway. Mount St. Helens sits at watch. It was raised from advisory 3 weeks ago when the deep tremor shifted upward and the microseismicity crossed 180 events per day. The threshold for warning is clear on paper but murky in practice, and volcanologists argue over whether increased gas flux alone justifies the jump or whether magma must be proven to be rising within 5 kilometers. Right now, the answer depends on interpretation. The deformation models fit both shallow hydrothermal pressurization and mafic intrusion at 6 kilometers. The seismic data lean toward magma but don't prove it. So the mountain stays at watch, while scientists weigh probabilities, recalculate depths, and wait for one more unambiguous signal. But behind closed doors, geologists are drafting the warning level statement. The public silence. If you drive through Cougar, Washington, 11 miles from the crater, you'll find gift shops open and hiking permits still being issued. Tourists walk the Johnston Ridge Observatory Trail. Fishermen cast lines into the Toutle River. The parking lots are full. There's been no evacuation order, no road closures, no public alarm. Local news ran a short piece on the earthquake swarms 2 weeks ago and moved on. The scientists are watching the mountain break itself apart in real time, and the people who live in its shadow mostly don't know. Part of this is caution. The USGS won't sound an alarm without certainty, and volcanic systems resist certainty until the moment they don't. Part of it is precedent. 40 years of small eruptions and steam vents that fizzled into nothing. And part of it is the curse of steady escalation, where each new threshold becomes the new normal, and urgency dissolves into routine. But a press conference has been scheduled for next week. Something is about to go public. The economic shadow. The Weyerhaeuser timber operation controls 224,000 acres around St. Helens, a forest economy worth $340 million per year. The Swift and Yale hydroelectric dams sit downstream, generating 619 megawatts for 190,000 homes. Mount St. Helens National Volcanic Monument pulls 360,000 visitors annually, feeding hotels, restaurants, and guide services across 3 counties. An eruption doesn't just stop traffic, it collapses supply chains. Interstate 5, the West Coast's main artery, runs 50 miles west of the crater and would close under half an inch of ash. The ports of Longview, Portland, and Tacoma handle 91 million tons of cargo each year, all vulnerable to ashfall that clogs machinery, shorts electrical grids, and grounds every flight in a 300-mile radius. Insurance models don't price volcanic risk well because the last major eruption predates modern actuarial tables. The economic disruption spreads in waves, first locally, then regionally, then through semiconductor and agricultural exports that depend on West Coast logistics. The systems are fragile in ways no one thinks about until the ash starts falling. But the real cost isn't measured in dollars, it's measured in what gets buried. The ashfall forecast. The computer models run thousands of simulations, each one tracing a plume of ash as it climbs and spreads. The wind aloft typically blows east, carrying the column over the Cascades and into the high desert beyond. A moderate eruption, column height 15 kilometers, deposits 5 centimeters of ash in Yakima within 6 hours. A larger event, 25 kilometers column, buries eastern Washington under 30 centimeters or more. At 10 centimeters, roofs begin to collapse under the weight. At 2 centimeters, car engines choke and die, air filters clogged in minutes. Water treatment plants shut down, their intakes fouled with abrasive glass particles. Hospitals fill with respiratory cases. The ash is not inert. It's hydrofluoric acid, clinging to jagged silica shards, and it turns every rainstorm into a caustic slurry. The forecast maps show concentric zones of fallout, probabilities shaded in gradients of gray. But the models can't predict the exact wind on the day, the precise column height, the duration of the eruption. They show you the possible, not the certain. But ash is survivable. The pyroclastic flows are not. The flow paths. The valleys radiate outward from the crater like spokes, carved by ancient floods and filled now with rivers, roads, and narrow stretches of development. Pyroclastic flows obey gravity. They pour downhill at speeds exceeding 100 miles per hour, a boiling avalanche of rock, gas, and ash, heated to 700 degrees Celsius or more. Nothing organic survives contact. Trees explode, cars melt, concrete crumbles. The flow itself is a density current, heavier than air, hugging the ground as it accelerates down the slope. It follows the path of least resistance, funneling into drainages, amplifying as tributaries merge. When the front hits snow and ice, the heat flash melts thousands of tons of water in seconds. The flow transforms mid-descent, becoming a lahar, a concrete thick torrent of mud, boulders, and splintered timber. The transition is seamless. What starts as fire becomes flood, and the flood travels farther, faster, with more inertia than the flow itself. The channels are predictable. Scientists have mapped every valley, every bend, every confluence. The Toutle River Valley, still scarred from 1980, is in the direct line again. The lahar legacy. On May 18, 1980, the lateral blast triggered a lahar that roared 50 miles down the Toutle River in less than 2 hours. It stripped forests to bedrock, snapped steel bridges, and buried Highway 504 under 6 meters of mud. The flow was so dense, it carried boulders the size of houses. Eyewitnesses described a wall of gray moving through the valley, silent at first, then deafening. The sediment didn't stop at the mouth of the river, it continued into the Cowlitz, then the Columbia, choking shipping channels and raising the riverbed by several meters. Dredging operations continued for years. The Toutle itself became a monument to the violence, its banks unstable, its floodplain a desert of ash and stumps. Vegetation returned slowly, in patches, but the river never regained its old course. Lahars don't require an eruption to be catastrophic. A collapse of the rebuilt dome, triggered by an earthquake or steam explosion, could mobilize enough loose material to generate a deadly flow. The threat persists as long as the edifice is unstable. But the snowpack this year is heavier than it was in 1980. There's more to melt. The glacier threat. Look up at the peak, and you'll see thin ribbons of white clinging to the slopes. Glaciers grew back inside the crater after 1980, cradled in the shadow of the dome, and older ice still hangs on the outer flanks. It looks serene, almost delicate. It's frozen water, waiting for a reason to move. That's the quiet trap of it. The same ice that softens the mountain's outline is fuel. Heat from an eruption doesn't just melt snow, it turns solid glaciers to water in minutes, and that water has to go somewhere. It goes down, and it takes rock, ash, and mud with it. Every ton of ice on those slopes is another ton of volume added to a lahar that's already unstoppable. The mountain's beauty and its weapon are the same thing. Glaciologists calculate enough ice to generate lahars reaching 50 miles downstream. The downstream cities. Follow that 50-mile line and you start reading names off a map. Toutle sits closest, right along the river that carries the mountain's runoff, then Castle Rock, then the paired cities of Longview and Kelso, tens of thousands of people living where the valley opens wide and flat. Threading through all of them is Interstate 5, the spine that carries traffic from California to the Canadian border. Rail lines run beside it. The Columbia River shipping channel moves cargo out to the Pacific just downstream. It's a knot of arteries, all crossing the same low ground. A major eruption wouldn't just bury a town. It would cut the north-south lifeline of the entire Pacific Northwest, severing road, rail, and river in a single afternoon. But the danger doesn't stop at the Columbia. The ash does. The aviation threat. Ash rises where roads and rivers can't follow. And in the air, volcanic ash and jet engines make a terrible pair. The fine glass particles melt inside a hot engine, then re-solidify on the turbine blades, choking off airflow until the engine simply stops. It's happened before. Aircraft have lost all engines mid-flight after wandering into an ash cloud, gliding in silence while pilots relit them one by one. St. Helens sits beneath busy air corridors linking the west coast to Asia and beyond. An eruption would push ash straight into those lanes. Flights would ground across the region. Travelers would strand in terminals, cargo would back up, and the delays would ripple outward for days. But planes can be rerouted. The people on the ground cannot. The monitoring dilemma. The seismologists watch their screens in shifts now, 24 hours a day. Each tremor gets catalogued, each GPS tick analyzed, each gas reading compared against the models. But the models can only say what's probable, not what's certain. Volcanic unrest has false started before. In 1998, swarms beneath the mountain continued for 6 months, then stopped. In 2004, the dome-building eruption began suddenly, after weeks of escalating quakes, but it was small, controlled, almost polite. The current data looks nothing like 2004. The weight of 1980 sits in every decision. 57 people died because the mountain gave signals no one had seen before, because the bulge grew in a direction the models didn't predict. The scientists know they'll be judged not by how many false alarms they issue, but by the one they miss. Volcanoes don't follow schedules. The magma moves when pressure and pathways align, not when the calendar says it should. Unrest can simmer for years or explode in hours, and the data never says which. At last week's meeting, the team voted. The consensus was unanimous. The consensus. An eruption is coming. Not likely, not probable. Coming. The question is no longer if the mountain will erupt, but when and how large. The seismic swarms have crossed the frequency threshold seen before every major eruption in the Cascade Range over the last century. The deformation has reached 11 centimeters, triple the rate of any non-eruptive cycle. The SO2 flux is now 450 tons per day, a number that marks magma within 2 kilometers of the surface. Every historical analog, every model, every dataset points the same direction. The mountain is primed, the system is pressurized, the pathways are open. The only variables left are timing and magnitude. This is what the researchers have been tracking in silence for 8 months. The pattern they couldn't announce until the statistics became undeniable. The evidence is no longer emerging. It has arrived. But even with consensus, the hardest question remains unanswered. The timeline uncertainty. When? The data says soon, but soon in geologic time can mean tomorrow or next year. Volcanic unrest doesn't follow a countdown clock. Redoubt in Alaska showed precursory swarms for 8 months before its 2009 eruption. Pinatubo in 1991 escalated in just 3 weeks. Mount St. Helens itself gave 2 months of warning in 1980, but the final landslide happened in seconds, triggered by an earthquake no model predicted. The current unrest could continue at this level for months, a slow tightening that gives ample time to prepare, or it could spike tonight. The seismic network can tell you the mountain is moving. It cannot tell you the hour. Forecasting the timeline requires a signal that hasn't appeared yet, a shift in the pattern that marks the final stage. The researchers are waiting for it, watching for it in real time. But one signal, if it appears, will narrow the window to days. The final precursor. The signal geologists watch for isn't another surge of tremors, it's the opposite. After weeks or months of building seismicity, the mountain falls silent. The earthquakes stop because the magma has stopped breaking rock. It's found its path. Pressure equalizes. The conduit opens. The ascending column of molten rock moves through fractures it's already carved, rising without resistance. What looks like calm to the outside world is the volcano clearing its throat. In 1980, the seismicity at Mount St. Helens dropped sharply in the hours before the landslide. In 2004, Mount St. Helens went quiet for 36 hours before the dome-building eruption began. The silence is not relief, it's the countdown. This morning, the seismometers went quiet. The silence. For the first time in 14 weeks, the network shows minimal activity. The drumbeat tremors that rattled the crater floor every 8 minutes have stopped. The shallow swarms beneath the north flank have gone still. To someone checking the public dashboard, it looks like the mountain has settled. But volcanologists know this pattern. They've seen it in the precursor catalogues of a dozen stratovolcanoes. Pinatubo, Redoubt, Unzen. The seismic noise drops because the magma is no longer forcing new cracks. It's moving through pathways that are already open, rising in a coherent column toward the surface. The silence has lasted 19 hours. Field teams are checking the instruments, ruling out equipment failure. Every sensor is functioning. The mountain isn't broken, it's ready. But the silence isn't empty. The GPS stations are still moving. The deformation continues. The benchmarks on the crater rim are displacing outward at 11 centimeters per day, 3 times faster than the peak rate recorded in March. The summit is inflating. Tilt meters show the entire edifice is swelling, the cone deforming under pressure from below. Magma is ascending without breaking rock because the rock is already broken. It's forcing the final kilometers through a plumbing system excavated by past intrusions, widening the conduit, pressurizing the shallow crust. The vent is clearing, gas is separating from melt, the column is becoming buoyant. INSAR data shows a bullseye of uplift centered 800 meters beneath the 1980 crater. The deformation pattern matches a shallow dike propagating vertically, less than 1 kilometers from the surface. The crust above it is thinning, stretching, approaching its mechanical limit. The models predict the surface will fail within 72 hours. The evacuation order. The order comes at 3:47 a.m., transmitted across every channel. Sirens echo through Toutle, Kidd Valley, the smaller towns hugging the river valleys. Emergency alerts light up phones in darkness. The same message repeating. Mandatory evacuation. All zones below 1,200 feet. You have 6 hours. By dawn, I-5 is a crawl of headlights stretching 40 miles south. Shelters open in Longview, Portland, Kelso. The Red Cross stages supplies in gymnasiums. National Guard checkpoints go up at the zone boundaries, turning back the curious, the journalists, the ones who forgot something and want to go back. Entire neighborhoods empty in hours. Pets loaded into cars. Photo albums grabbed from mantles. A lifetime compressed into what fits in a trunk. The grocery stores have already been stripped. Gas stations run dry by noon. This is the machinery of disaster response, and it moves with surprising speed once it finally begins. But not everyone will leave. Some never do. The holdouts. In 1980, Harry Truman stayed at his lodge on Spirit Lake. 83 years old, he'd lived there for 54 years. When the evacuation orders came, he refused. Told the reporters he'd been through eruptions before, that the mountain was his home, that he'd take his chances with 16 cats and a lot of whiskey. They found his lodge site under 150 feet of avalanche debris, still buried today. He wasn't alone in staying. Dozens refused to leave the red zone, some out of stubbornness, some out of disbelief, some because they simply couldn't imagine the scale of what was coming. 57 people died that morning, many of them far outside what anyone thought was the danger area. There's something deeply human in that refusal, the inability to accept that the ground beneath you might betray you, that the landscape you've known your entire life could vanish in minutes. We are pattern-seeking creatures. We expect tomorrow to look like yesterday. The data says otherwise, but data is cold, and the mountain has always been there. The mountain doesn't wait for consensus. It doesn't negotiate. The inevitable. St. Helens has erupted, on average, every 100 to 300 years for the past 40,000 years. The 1980 event was not an anomaly. It was routine, geologically speaking. The mountain builds, collapses, rebuilds. The cycle has repeated itself at least 20 times in recorded geologic history, each time reshaping the landscape, each time erasing what came before. The current unrest, whether it leads to eruption now, or in 5 years, or in 50, is just one frame in a film that's been running since before our species learned to speak. The Cascade Range has been volcanically active for 36 million years. Rainier, Hood, Shasta, each one a monument to the same slow, grinding collision that builds them and tears them down again. We live on a planet that is not finished. The crust beneath the Pacific Northwest is still diving under North America at 4 centimeters per year. Magma is still rising. The mountains are still growing. In 100,000 years, St. Helens might be twice its current height, or it might be gone entirely, replaced by a different vent in a different location. This is not a disaster. It's just geology. But knowing it will happen and watching it happen are different things entirely. The waiting. Right now, seismometers hum in the silence. GPS stations record fractional shifts every 15 minutes. Cameras watch the summit through thermal and visible light, capturing nothing but snow and steam. In Vancouver, scientists check the same data streams they've checked for weeks. In towns around the mountain, go bags sit by front doors. Evacuation routes are memorized. Hotel rooms 50 miles out are booked solid. The mountain has risen 8 centimeters. The magma chamber has expanded. Every model says the same thing. But the flanks are quiet, the glaciers still, the forests undisturbed. This is the space between knowing and experiencing, between prediction and reality. Hours stretch, days blur, everyone watches, and in that waiting, we glimpse what our ancestors must have felt, watching mountains they thought were eternal begin to move. The deep time. Mount St. Helens is 40,000 years old. In the lifespan of the Cascade Range, it's an infant. Mount Rainier is 500,000 years old. The subduction zone that feeds them both has been grinding for 37 million years. St. Helens will erupt hundreds more times. It will build new cones, collapse into new craters, spill fresh lava across valleys that don't exist yet. In 2 million years, the plate will shift north, and the mountain will go cold, its magma supply severed. The 1980 eruption is a single frame in a film thousands of hours long. What's happening now is another frame. Your life, everyone you know, every empire that rose and fell, all of human civilization fits into a few seconds of that film. From that vantage point, this eruption is routine, unremarkable. Just the mountain doing what mountains do. But we don't live in deep time. We live in the moment when the mountain wakes. The human scale. There's a family in Toutle River Valley finishing dinner. The youngest asks if the mountain will explode tonight. No one has an answer. In a command center 50 miles south, a scientist rechecks the seismic data for the 11th time today, looking for the pattern that means it's starting. Emergency responders are staged at 3 locations around the restricted zone. Their vehicles are fueled, their radios are charged. Some of them remember 1980. They were children then, watching ash fall like snow, watching the sky turn black at noon. A retired logger in Castle Rock keeps a photo on his mantle. His father, standing in front of a grove of old-growth Douglas fir, 1979. The grove is gone now, buried under 600 feet of debris. He wonders what will be buried this time. These are the hours geology intersects with lives, when deep forces meet fragile routines, when the patient indifference of the Earth presses against the urgency of the present. But the story isn't over. It's just beginning. The unpredictable, because for all the seismometers and GPS arrays, for all the gas samplers and thermal cameras, the mountain still holds secrets. Eruptions surprise us. The 1980 blast came from the north flank when experts expected a summit vent. Pinatubo in 1991 had been dormant for 500 years before awakening with 10 days warning and unleashing the second largest eruption of the 20th century. St. Helens might vent gently through a new lava dome, releasing pressure in a decades-long sequence like it did from 2004 to 2008. Or it might explode catastrophically, tearing open a new flank in seconds. Or it might stop. The magma could stall, cool, crystallize. The mountain could go quiet again for a generation. Science narrows the uncertainty. It cannot eliminate it. We map the probabilities, but the Earth writes the outcome. Every volcano is a unique experiment. Every eruption a singular event. And perhaps that's the real lesson St. Helens teaches. The living planet. Not that the planet is dangerous, though it is. Not that we're helpless, though we're small. But that the Earth is alive. Dynamic in ways we forget in our daily routines. Creative and destructive in the same breath. Building mountains while tearing them down. Shaping climates, cycling elements, renewing the surface. St. Helens is a window. Through it you see the engine that built continents. The same process that formed the Cascades 40 million years ago is running now, beneath your feet, in real time. The Juan de Fuca plate sinking into the mantle, rock melting at 100 kilometers depth, magma rising through the crust. Fear and wonder coexist here. You can evacuate the blast zone and still marvel at the forces in play. You can respect the danger while recognizing the volcano as evidence of a planet capable of sustaining life precisely because it is restless, because it recycles itself, because it never truly sleeps. But understanding doesn't remove the danger, it deepens the respect. The payoff. What is happening beneath Mount St. Helens is not a mystery. It's a convergence. Deep magma injection at 8 to 12 kilometers, feeding lateral intrusions that are fracturing the north flank. Phreatic pressure building in the hydrothermal system as groundwater boils against rising heat. A cryptodome growing in the same weak zone that failed in 1980. Each element is known. The seismic swarms, the uplift, the gas signatures. They fit a pattern volcanologists have studied for decades. The timeline is uncertain, the exact trigger unknowable until it happens, but the trajectory is clear. This is not the mountain getting worse in some vague sense. It's the mountain progressing through a well-understood eruptive sequence. And we are watching it unfold with unprecedented clarity. More instruments than ever before, more data, more models, more time to prepare. The eruption, when it comes, could rival 1980 in complexity, if not scale. It could be smaller, it could be larger. What we know is this: the mountain is awake, the magma is moving, and somewhere beneath the snow and rock, the Earth is writing the next chapter. The real question, isn't whether Mount St. Helens will erupt again, it's whether we'll be ready when it does. Not just with seismometers and satellite data, but with the humility to remember that we live on a planet that doesn't pause for us. The instruments will keep listening, the magma will keep rising, and we'll keep watching, knowing that the mountain operates on a timescale we can measure but never control. If you want to explore more stories like this, from volcanoes to deep time to the forces that shape our world, there are more waiting for you here. Subscribe if you'd like to come along. For now, the Cascade Arc sleeps lightly, the subduction continues, and beneath the snow, the Earth remembers what we sometimes forget. This world was never still.